Welcome, students. I'm so glad you could join me today for the very first explainer of our software engineering course. We are jumping right into a foundational concept today, one that is absolutely crucial and will carry you through your entire degree and, honestly, well into your professional careers. And that concept is this: system architecture relies entirely on context. Software engineering is definitely not a one-size-fits-all discipline. You simply cannot build every program utilizing the exact same blueprint. The design, the safety checks, the architecture we choose, it all depends completely on the specific type of system we're producing. So to really wrap our heads around this, we're going to dive into 4 vastly different case studies right from your textbook.
Here is our agenda for today's session. We'll quickly cover why there is no one-size-fits-all software, and then we're going to explore 4 unique case studies: an insulin pump, the Ment Care system, a wilderness weather station, and the iLearn portal. Finally, we'll wrap up the whole thing with a comprehensive chapter summary to help you prepare for those upcoming exams.
All right, let's get into Section 1, No One-Size-Fits-All Software.
Now, a really common misconception for beginners is that learning to code means you can build absolutely anything exactly the same way. But think about it for a second. You wouldn't build a safety-critical medical device utilizing the same program architecture as a web-based student portal, right? If a school portal crashes, well, it's an inconvenience, usually right before an assignment is due. But if a medical device crashes, the consequences could literally be fatal. The environment, the users, and the cost of failure completely dictate how we engineer the software. And that brings us perfectly to our first case study, which is the insulin pump control system. But before we get to the pump itself, let's define what we mean by an embedded system. An embedded system is a software-controlled system that is embedded as a controller inside a hardware device. These are very often safety-critical, meaning they must operate with incredibly high reliability. Our case study is a software-controlled insulin pump used by people suffering from diabetes. Essentially, this embedded system simulates the human pancreas. It has to constantly monitor blood sugar and then deliver the exact correct dose of insulin to keep the user safe.
Let's examine the hardware architecture of this pump. Starting over on the left, we have the blood sensor. This sensor actually measures the electrical conductivity of the blood, which correlates directly to the user's blood sugar level. This raw reading is then sent straight to the central controller. You can think of the controller as the brain of the operation. It's driven by a clock to ensure very timely, regular checks. If it decides insulin is needed, it sends a signal to the miniaturized pump to draw from the insulin reservoir and deliver it through the needle assembly. Oh, and notice it also features an alarm system. This is absolutely essential to warn the user if something goes wrong. Every single piece of this hardware relies completely on the embedded software to function flawlessly.
So, how does the software actually process this information? Well, the program utilizes a strict sequential activity model. It's very logical. Step 1, it analyzes the raw reading coming in from that blood sensor. Step 2, it computes the actual blood sugar level based on that reading. Step 3, it calculates the precise insulin requirement by looking at the current reading, comparing it to previous readings, and determining the rate of change. And finally, Step 4, it translates that calculated requirement into a very specific sequence of commands sent to the pump. For instance, if it needs to deliver 10 units, it might send exactly 10 electrical pulses to the pump. It's a highly logical, step-by-step transformation of data into physical action. Because, let's be honest, guessing is not a feature you want in a robotic pancreas.
Because this is a safety-critical system, the absolute primary architectural requirements here are availability and reliability. This table brilliantly illustrates how we manage risks in software engineering. Take an overdose computation. That has a high estimated risk and is classified as intolerable. This means the software architecture must guarantee this practically never happens, maybe by adding a hard-coded maximum dose limit that the system can't override. Then we have hardware failure, which is classified as ALARP. That stands for as low as reasonably practical. We try to minimize it as much as humanly possible, but at the end of the day, we can't defy physics. Parts wear out. Finally, an allergic reaction is classified as acceptable. Why? Because the software simply cannot prevent biology, and the result is usually just minor skin irritation from the needle. To summarize our first study, the insulin pump is a closed, embedded system where physical safety and absolute reliability are the main driving forces behind the architecture.
Moving right along, Section 3, Case Study, the Ment Care system.
So our first system was about physical safety. Ment Care is a totally different beast. It's what we call an information system. By definition, an information system manages data, typically using a centralized database, to support organizational operations and reporting. The Ment Care system specifically manages medical records for patients dealing with mental health problems, and it has a dual purpose.
First off, it generates administrative and management reports so the health service can track overall performance and costs. But second, and much more crucially, it provides doctors and nurses with timely clinical data to actually support patient treatment.
Structurally, Mentair relies on a client-server architecture. You have local client computers connected over a network to a central Mentair server and patient database. But here is the really crucial architectural twist for this specific system. Mental health clinics are very often held in local community centers where network connectivity might just drop unexpectedly. Because of this, the system is purposely designed to allow clinical staff to download a secure, local copy of patient records directly to their laptop. This means they can continue to view patient histories and prescribe life-saving medication even if they are completely disconnected from the main network, and they can just sync the data back up later when they're back online.
However, this incredibly useful offline capability creates the core architectural conflict of the entire Mentair system. Let's look at the tension here. On the left side, we have strict legal privacy requirements. Mental health data is incredibly sensitive. Any unauthorized access is a severe breach of the law. Now, privacy is easiest to maintain if there is only one heavily guarded central copy of the data. But on the right side, we have the critical need for data availability. If a patient is in a crisis, the doctor must have immediate access to their file, which requires those multiple local copies on laptops. As a software engineer, your job is to design an architecture utilizing heavy encryption, local database locks, and strict access rules that perfectly balances this massive tension between privacy and availability. To summarize, information systems like Mentair are driven entirely by the complex balancing act between keeping data secure and keeping it operational.
All right, let's switch gears again. Section 4, Case Study, the Weather Station. The Wilderness Weather Station is a classic example of a sensor-based data collection system. What does that mean? It's software that runs autonomously to collect environmental data from various sensors, things like wind, rain, and temperature, and then transmits all that data to other systems for processing. The overarching goal for this specific project is deploying hundreds of these stations out into remote, hostile environments to monitor climate change. Because they are so remote, sending a human out to fix them is incredibly difficult and expensive, and that fact completely changes our software priorities. So the weather station doesn't just operate in a vacuum. It operates as a system of systems. It's like a giant interconnected puzzle. On the left, we have the actual weather station system itself, out there collecting data in the wilderness. It has to communicate with the data management and archiving system, which is the system that actually processes and stores the data for the scientists back in civilization. But it also communicates with the station maintenance system. This system monitors the hardware's health and can even remotely update the embedded software. So our lone weather station is really just one node in a much broader data ecosystem.
What you really need to take away here is how the harsh environment literally dictates the software design. First, the station runs entirely on battery and solar power. Second, it communicates via a very, very slow satellite link. This means the software can't just blindly stream raw data constantly. It has to process and aggregate it locally first just to save bandwidth. Furthermore, the software must actively manage its own power. For instance, it might need to shut down delicate sensors during violent storms so the station isn't destroyed by the exact weather it was built to monitor. Finally, it requires dynamic software reconfiguration. If a component fails or needs a software patch, we have to push those updates remotely over that incredibly slow satellite link without taking the entire station offline. To summarize, data collection systems out in the wild are architected entirely around power conservation and autonomous remote management.
Moving on to our last example, Section 5, Case Study, the iLearn Portal.
The iLearn portal is a web-based system used in schools, very much like the university systems you are probably using right now. System-wise, it functions as a support environment, specifically a service-oriented system. It pulls together 3 distinct types of services. First, we have utility services, like your basic authentication and email. Second, application services, like document sharing or testing tools. And third, configuration services that adapt the environment to specific users or specific courses. Now, as an engineer, you must understand how these services interact. Integrated services communicate directly with each other under the hood utilizing APIs, creating a really seamless experience for the student. Independent services, on the other hand, are just accessed alongside each other via a web browser, and they often require the user to manually share or copy data between them. To summarize our final study, support environments like iLearn feature highly distributed, flexible architectures built to integrate a wide variety of services for mass access.
Let's bring it all together. Section 6, Chapter Summary and Exams. Huge congratulations on making it through Part 1's introduction. Before we close out, let's summarize the key takeaways you absolutely must know, especially for your upcoming exams. First, as we've clearly seen today, architecture heavily depends on the system type. You must be able to define and differentiate an embedded system, an information system, a data collection system, and a support environment. Second, remember that software engineering is not just hacking together some code in a basement. It is a rigorous, structured process involving specification, development, validation, and evolution. Third, software is so much more than just code. It impacts human lives every single day. This means ethics and professional practice play a crucial foundational role in our decisions. Most importantly for your exam, be prepared to compare these 4 case studies. If a test question asks why you can't build a safety-critical insulin pump using the loosely coupled architecture of a web portal, well, you now have the tools and the vocabulary to answer that comprehensively.
To wrap up, I'll leave you with this final provocative thought to ponder. How will these architectural differences influence your own personal approach to system design as we step into Chapter 2? Next time you sit down to write a program, I want you to ask yourself, what is my context? Who is actually using this? And what happens if it fails? Because understanding the environment is the first true step of software engineering. Thank you so much for joining me for this explainer. Study hard, and I will see you all in the next session.